Correlation 12.1. A researcher wishes to examine the relationship between years of schooling completed and the number of pregnancies in young women. That's funny. Her research discovers a linear relationship. And the least squares line is y equals 5 minus 3x, where x is the number of years of schooling completed and y is the number of pregnancies. The slope of the regression line can be interpreted in the following way. Now that probably sounds like a bunch of craziness. All right, let's write that down and slowly talk it out. So y equals 5 minus 3x. So what is x? X is the number of years of schooling. So, and I guess that means beyond college, beyond high school. I'm assuming, because otherwise, if you plug in like a 12 years just for finishing high school, that'd be 5 minus 36. That'd be a negative number of pregnancies. I don't think that makes any sense. So I assume that x is number of years of school in college. All right, and y is the number of pregnancies. I don't know why they said pregnancies. It's kind of weird. Why didn't they just say kids? Anyway, it's kind of a weird sounding question to me. Right, so in other words, you get the idea. Basically, if you plug in, let's say a young lady did 1 year of college. This equation would predict that she would have how many kiddos? I know, but that just sounds weird to me. I'm going to say kids.
We could have 2 kids.
I know it's not exactly the same, but it still just bugs me. So I know you're right. So it's just weird. I think it's weird. 5 minus 3 is 2. Right? See what's happening there? This is kind of a strange equation for many reasons, but let's get the hang of what it's saying. So it's saying if you plug in the number of years of college, x, y will tell you the number of pregnancies. I'm just saying kiddos. So, right, so plug in 1, right? 5 minus 3 times 1, 5 minus 3, 2. Meaning, on average, women that spend 1 year in college have 2 kiddos. That's a crazy equation. Because then if you go to 2 years in college, what? You're not going to have any kids? I mean, that's just negative kids, whatever that is. Yeah. Right, that'd be 5 minus 6, right? That'd be negative 1. This is kind of a wacky equation. It's really wacky. Anyway, that's what it's supposed to do. What a strange... I didn't look closely at this example. What a strange example. Anyway, all right. So that's the idea, though. You getting the idea? That's what this chapter is about, is pregnancies and years in college. No, that's not what this chapter... This chapter is about 2 variables connecting. How an equation is a relationship, a connection between 2 letters, 2 variables. In this case, kind of strange ones, years in college and number of pregnancies. All right. So, therefore, they're going to ask us a question. They're saying the slope of that equation can be interpreted in the following way. Well, first off, what is the slope of that equation? Where's the slope? Yeah, it's the number next to x. Do you know that from your algebra days? Did you take some algebra in high school? Were those the best days of your life? Or maybe you took some in college recently? They were Zach's best days. He loved them, right? He took me for algebra. All right. He won't say otherwise as long as I'm around. All right. So slope's minus 3. So now... you can turn minus 3. Remember how, well, maybe you don't. Do you remember a slope is rise over run? You might remember that. Slope is rise. Maybe I better put it down here. Slope is rise over run. It's how steep a line is. Rise over run. So the slope is negative 3, and then you just put it over 1. Now, why do I just put it over 1? Well, because what is 3 divided by 1? It's just 3. Or negative 3 divided by 1 is just negative 3, huh? In other words, dividing by 1 changes nothing. So you can imagine a 1 down there and it won't change anything. You tracking with me? This is just a fancy way of saying negative 3, isn't it? Negative 3. If you divide by 1, nothing changes. 1 goes in there 3 times, or negative 3 times. Right? Now, why do we, okay, great, but why do we do such a weird thing? Well, because we need a number for the top to be our rise and our bottom to be the run. That's what slope means, rise over run. So that means this equation is changing. This is the rise. So rise is change in y. Y-axis goes up. I'm doing a lot of algebra background here. The y-axis goes up and down. Glad to see my former algebra students are nodding right along with me. All right. Yes. Right? So that's y, and this is change in x because it's run. Run is sideways on a graph. So we're not going to go deep into this. If you're feeling like totally lost, don't worry. There's not much of this. This is just for a second, and we'll get back to normal stats. They're not going to ask us a lot of this algebraic kind of stuff. But on this one they are. So change in y over change in x. That's what rise is up and down, run is sideways, means. So what does that mean? Negative 3y. What is y again? Pregnancies. Minus 3 pregnancies. See, that's just weird. For every one added year in college. Every year you're in college, it costs you 3 kids. That's crazy. That's a crazy equation. It didn't work out that way for my wife. She spent 5 years in college and had 5 kids. Anyway, so this is certainly not the truth, but this is their little made-up equation. So, all right. So get what they're saying though. The slope is always the number next to x. It's not the other number. So I probably should have said that. Slope is the number next to x. That's why I grabbed the negative 3 right away. And then you write the slope as a fraction. You put it over 1. That's what I did here. And then remember, it's change in y over change in x, because it's rise over run. That's what slope always means. So y is pregnancies, right? They just told me y is pregnancies. And x is years in college. So that means she loses 3 pregnancies, right? Negative 3, goes down 3 pregnancies for every year in college. So let's see, how do they say it? When amount of schooling increases by 1 year, the number of pregnancy tends to decrease by 3. Yeah, exactly. Which is crazy. But that's what their little equation is saying. Does that make sense? Kind of strange? I mean, for a lot of reasons. All right, let's move on. Number 2. If the linear correlation coefficient between the explanatory variable x and the response variable y r is 0.4, the slope of the regression line is, okay, I haven't given you any of this information, right? They're just jumping in with all this stuff. What are we doing? I probably better back up and just say, what are we even doing in this chapter? What we're doing in this chapter, we actually introduced it, but it's been like 2 months since I actually did an introduction way back in their first exam. We're looking for how 2 variables relate. Remember how we talked about, what if I was to do this? What if I was to go all over campus and I was to ask people, hey, how many hours do you study every week? And then also, what's your GPA? If I was to go all over campus and the first person say, okay, I study 10 hours a week, my GPA is 2.3. Somebody else say, I study 15 hours a week, my GPA is 2.9. Somebody else say, well, I study 20 hours a week, my GPA is 3.2. I study 30 hours a week, my GPA is 3.8. I study 2 hours a week, my GPA is 2.1. On and on you go. I could just keep asking people all over campus how many hours they study per week and what their college GPA is. If I did that and then I made a graph of hours of studying per week on the x-axis and GPA on the y-axis, and I started putting the dots down. Remember how to graph things? Again, I'm referring to your algebra days. Do you remember that a little bit? Like this is like an x and this is a y. This is the x-axis and the y-axis. Do you remember that a little bit? Sort of? So go over 10 and up 2.3. So you go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Go over 10, and this would be like 4.0 here, and then halfway is 2.0. This is 1.0 and 3.0. So over 10 up 2.3, like about right there. There would be the dot over 10 up 2.3. Is that making sense? Remember graphing over and up from your algebra days, like X, Y, you go over and then up. So over 10 up 2.3. Let's do another dot. Then I'll do the over 15 up 2.9. So if you go all the way to 15, this would be 11, 12, 13, 14, 15. So there's 15 up a little higher, 2.9. So about right there. There's over 15 up 2.9. How about the next one? Over 20 up 3.2. 16, 17, 18, 19, 20. There's 20. Up 3.2. That'd be about right there. So that's over 20 up 3.2. This one, over 30 up 3.8. So I'll see if I can find over 30. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. Up 3.8. So it'd be about like right up there. So that's over 30 up 3.8. Anyway, I skip, and then this one, I'm just tired of doing it. But well, over 2 up 2.1. It's about right there. Over 2 up. So anyway, I just put those dots on a graph. Wait a minute, I messed that last one up. What was that one? That was over 2 up 2.1. Anyway, is that one. So I put those dots on a graph, and what do you notice about those dots? Yeah, they kind of make a line, don't they? Not exactly, they're not exactly lined up, but they're sort of lined up. And if I kept going all over campus and asking people and putting their dots on a graph, we're going to do that tonight on our calculator, and there'd just be a bunch of dots, probably kind of, sort of in a line. They wouldn't be perfect, right? But they would probably sort of be a line that goes up, because probably generally the more you study, the higher your GPA. There's exceptions. There's harder majors and other kind of things. But in general, right? Okay, so they would have what we call a positive relationship, wouldn't they? They would be going up to the right. Well, we have something called R, which our calculator is going to give us tonight. It's called the linear correlation coefficient. And what it is it's a measure of how well those dots fit in a line. Do you know what I mean? Like if you have some dots that fit pretty close in a line like that going up, your R value might be something like 0.9. R goes between negative 1.0 and positive 1.0, with 0 being in the middle. R, that's R. R is always between negative 1 and positive 1. And the closer it is to negative 1 or positive 1, the more the dots form a perfect line upward, or if the dots are going pretty straight downward, that would be like maybe negative 0.9. If they go perfectly straight up, like right in a perfect line, that would be 1.0. If they go down in a perfect line, that would be R is negative 1.0. Are you tracking with me? It's making sense? So there's this thing called a linear correlation coefficient, R. And it always comes out to be a number between negative 1 and positive 1. And the closer it is to negative 1 or positive 1, the more that it makes a straight line. So if it's going up, it's positive, right? This is a positive, positive, and this is a positive. So the more the line is going up, if the line is going up, it's a positive R value. If the line is going down, it's a negative R value. And if it's a perfect line, it's 1.0. If it's close to a perfect line, it'd be like 0.9. Well, what would it be if you had a graph where the dots were just like crazy random and they didn't make a line at all? Well, then R would be about 0 or something close to it, maybe 0.1 or something pretty close to 0. So your calculator, we're going to be putting data into our calculator tonight. It's going to be a calculator intensive night. We're going to be putting data into our calculator, hitting a button, and it'll show us a picture of the dots, and then we'll hit another button, and it'll give us the R value. And you want to start to understand and feel those R values. The closer the R is to 1 or negative 1, the closer the dots are to forming a line. It's a measure of a linear correlation. Correlation is like a connection between the two variables. It's the linear correlation coefficient. All right, so on this problem right here, they're telling me that their R value, their R is 0.4. It's positive, so that's why I said there's a positive relationship. Let's go to the next one. This is question number 3 here. So they're giving me a bunch of dots. This is like a scatter. This is called a scatter plot. This is a bunch of data that is just scattered on the graph. So it's a scatter plot. 2 sets of bivariate, that just means 2 variables, bivariate 2 variables, with the same response variable. The first compares x and y, the second w and y. So this is x and y, this is w and y, okay. What do they want me to do about it? Oh, at the very bottom, or right down there by the bottom, it says, which explanatory variable has a stronger relationship with the response variable y? In other words, which one of them forms a tighter line? Which graph, the first graph or the second graph? Yeah, this one is a tighter line, meaning that x and y are tied together more tightly, right? So certain things are connected more than others, right? Like I said, if I did a graph of hours of studying, in all over campus and GPA, we'd probably find a pretty somewhat linear relationship. But what if I went all over campus and I asked people, what the first number, what's going on with my little pen here? All right, so what if I did the first number on your cell phone, right? We all have a first number on our cell phone. Mine's a 7. Would we find that people that have higher numbers on their cell phones also have higher GPAs? Yeah, no, not at all. If we went all over campus asking people, what's your GPA and what's the first number in your cell phone? And then we put those we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for the first number on their cell phone. We would just find crazy random dots, right? There's no connection between the number on your cell phone and your GPA, is there? That'd be ridiculous. Those 2 variables do not affect each other, is what we're saying. The number on your cell phone and your GPA have nothing to do with each other. What if I went all over campus asking people their GPA and asking them how many hours they work at an outside job per week? How many hours they have to work at a job per week? And their GPA. What would we find there? Yeah, what kind of correlation would it be? If you work more and more hours, it's probably hard to keep a good GPA. Of course, sometimes those people are really disciplined people too, but still, it's just hard. You just don't have as much time. We would probably find a somewhat negative relationship, right? More and more hours of work, probably. I think there might be a lot of exceptions to that. But in general, probably more and more hours of work, lower GPA, because you just don't have time to study. I remember I tried to take a couple classes after I had a full-time job and a couple of kids, and it was craziness. I don't know how some of y'all do it. I would show up at exams having not studied at all. I would drive out. Oh, and I'm a big baby about sleep. That doesn't work for me. I need my 7 hours, or I'm a big whiner. So I simply just didn't study, was the final. I would do my job, hang with my kids and wife, go to show up at class and go, wow, I have a test now and I haven't studied. That's different. I didn't used to do that back when I had no responsibilities but school. Anyway, so for me, I took a dive. So hours of work and GPA they did for me, have a negative relationship. All right, so we're talking about how things relate, right? This would be a R value that's negative, like negative 0.8 or something maybe. Pretty downward negative. This would be positive 0.9 or something. And this would be R that's about 0 because cell phone number and GPA have no connection. Okay, so getting back to the main question. So this one shows a stronger connection. It's a negative connection, isn't it? But it's a stronger connection than the other one. So the first variable has a stronger relationship to y, doesn't it? All right, on we go. Question 4. All right, so they want me to match up these. Is there one more? Just confusing the way it lays them out. So this is number 1, I guess. I'm going to put a line there. This is number 2. Hard to tell where they separate. This is number 3, I guess. Wait a minute, they all look alike to me now. I think this is number 4 here. This is number 3 again, isn't it? Am I doing that right? I think it is. And this is like the remnants of number 2 up here. All right, I did the best I could when I copied it. All right, so anyway, they want me to match up those. These are the R values with the various pictures. It's mix and match. All right, so let's do it. Let's grab this 0.7. Well, let's start with the one that's easy. How about the one that's negative almost 1? How's number 4 look? Yeah, number 4 is a nothing, huh? Yeah, it'd have to be that one, wouldn't it? This has got to be the negative, because that's going down pretty much a fairly tight line. That'd be the negative. It's going down, so it's negative. And it's almost 1, so it's a pretty tight line. So we got that one. Okay, what do you think about which one of these, 2 or 3, which one's a tighter line? 3 looks a little tighter. He's probably the 0.73, I guess. Is that what y'all are thinking? The positive, that's what I was thinking. Is that good? He's the positive, somewhat of a, it's a little looser. It's a little lower than the 9.3 was. All right, so how about the 0.10? Yeah, that's that 4th one, huh? Because that's just nothing. There's just no relationship. That's like cell phone and GPA or something, right? And then finally the negative 0.53, that'd be this one, or it's R. R equals negative point, because it's down a little bit, but pretty loose. Pretty loose in there. Is that good? Getting the feel of how R looks from a scatter plot? It's a measure of how tight the dots fit in a line, positive up, negative down. Goes between -1 and +1. Really important calculation. It's how people in the world determine if 2 things have a connection. All right, on we go to number 5. Here's a scatter plot set by variate data. What would you estimate the correlation coefficient to be for that one? 0. Yeah, that's a big 0. There's just no connection at all there. Right? Easy enough. On to number 6. The scatter plots below show the relationship between height, diameter, and volume of timber in 31 felled black cherry trees. The diameter of the tree is measured 4 feet above the ground. It's interesting. So we're getting real now. So this is height. So this axis right here is height, and this axis right here is volume. This is diameter and volume. So we're doing height versus volume and diameter versus volume. Okay, so what are their questions for us? Let's see. Here's the same second picture again. For question A, describe the relationship between height and volume of these trees. Let's go back to the height volume. So here's the height, this axis. Here's the volume. What are my options? Is it weak, moderate, positive, or is it strong positive? So this right here. What do those dots look like they're a positive slope? Strongly so or weakly so? Yeah, kind of a weak. That's a weak positive, isn't it? Looks like, yeah, generally trees that are taller, right, bigger height, have more volume. More total tree is there. That makes sense, right? The higher the tree is, probably there's more total wood there, more total volume of tree, right? But it's a weak positive, isn't it? So we'd say weak positive. And then part B talks about the volume diameter connection, diameter and volume. What would you say about that one? Yeah, this is a pretty tight line, positive. That's a strong positive, meaning the thicker the tree, they measured it at 4.5 feet, didn't they say? Yeah, 4.5 feet above the ground. The thicker the tree, the more wood is there, really, for sure, right? They really are connected. Stronger than height, right? Because a tree can be tall but thin and not have a lot of wood. That's a good example. C, suppose you have height and diameter measurements for another black cherry tree. Which of these variables would be preferable to use to predict the volume of timber in this tree using a linear regression model? So somebody was to say to you, all right, you've seen these two models. Here's volume versus diameter and volume versus height. And somebody was to come to you and say, all right, we got a whole bunch of other cherry trees. Well, we got one more cherry tree. And do you want me to tell you the height or the diameter for you to be able to predict how much wood it actually has? The diameter is way more helpful in figuring out how much wood it's going to have. There's a stronger connection between diameter and volume than height and volume, huh? That's what we're seeing on those graphs. You getting the feel of the usefulness of this? This is how we figure and quantify, give numbers to, the connection between two variables. And we can see in this example that diameter is a much better predictor of volume than is height for black cherry trees. All right, question number 7. The following table shows retail sales in drugstores in billions of dollars in the U.S. for years since 1995. Let S of T be the retail sales in billions of dollars. And if I have linear model, boom. Okay, so they give me some equation. What do they want me to do with it? Use the above scatter plot to decide whether it fits the data well. Was there a scatter plot? What scatter plot? Oh yeah. I'm looking for like lots of dots. It is that. Yeah. Thank you. I'm a little slow tonight. Yeah. It's those 5 dots. So they're such a line. I just thought it was a line. Yeah, they're very lined up, aren't they? So that's our 5 dot 6. There's 6. 6 dot scatter plot. Okay. So is it? Well, yeah. Well, clearly it's a good model, right? It fits those dots super well. So well I didn't even notice them. Yeah. All right. So then it says, estimate the retail sales in the U.S. in 2014. So how can you use this picture, this equation, to estimate the sales in 2014? Let me write out this equation for you. F of T equals 9 point, I'm just grabbing this thing right here, 9.44 T plus 84.182. Okay, now, what is T again? Years since 1995. So they're wanting me to estimate the year 2014. So in the year 2014, what is T going to be? Christina, you got it? What is it? 9? How are you coming up with that?
95 to 2014. Oh, wait.
I think you're doing 2005.
Yeah.
Yeah. So it'd be 19. Yeah. See what Christine's doing? She's right on the money. She's taking 2014 minus 1995 and getting the answer 19, right? Because T is how many years after 95. And so if it's the year 2014, subtract that, that's 19 years after 1995. And so what does that mean? Well, that means you plug in right there for T, 19. And then just hit the buttons on your calculator. Right? You're going to multiply by 19 right there. So it's going to become 9.44 times 19 plus 84.182. Is that making sense? Somebody got a calculator number there? What is it? 263.5? 54? We getting that? Coming out? So in other words, that's the equation of that line. Do you see what they're doing here? This is what we're going to do tonight. We're going to take a bunch of dots, fit a line to it. The calculator will do all that for us. We'll just hit the button. We'll just put in the data, hit the buttons, and it'll fit the line for us and give us this line equation. But then once we have that line equation, we use it for prediction purposes. See how business would use this? They would look at a trend. These dots are the trend, right? See these little dots here? These are the trend in the market. And then they use that to predict the future. They go, well, in 2014, of course, that's the past for us now. But if you could jump into the future, plug into that equation and predict, if it continues to grow at the same rate, what the sales are going to be in the year 2014, which is old history for us. 263 billion sales if it continues that way. Now, down here they want us to estimate the retail sales in the U.S. in 2014 and then use the model to predict the year that corresponds to 240. Yeah, so our first answer is the 263. I don't know how far they want you to round. Does it say?
It's just two decimal places.
Okay. $263.54 billion. Now, how are we going to do the next question? Write that a little better. The next question says, use the model to predict the year that corresponds to the retail sales of 248 billion. So what year, when will the market hit 248 billion? That's what they're asking. In what year will the market hit 248 billion? How do we figure that out? Yeah, I just let the equation equal 248 billion and solve for the t. You see that? We're doing a little bit of algebra here. So I'm gonna take this. This is the equation, right? This connects. Let's make sure we're clear on what this equation is saying. This equation connects dollars with years, right? This t is years. Cents, 1995, right? So that's how that equation works. You plug in, like what did we just do? We plugged in 19 for t, worked it out, and it came out to equal 263 billion. So you see, this equation, you plug in years, it'll give you how many billions of dollars will be made that year in retail sales. Or, vice versa, you could plug in the money you want and solve for the year. This is a connection between money and years. So we could use it either way. So in part B here, the second part, they're saying it equals 248 billion. So take the little equation and find the t, solve for this t to make this equation true. Does everybody see what I'm doing there? Am I losing you completely? It's a little more tricky step here. So I'm trying to answer part B. They're saying, in what year will it be 248 billion? In fact, I'm going to need to move it up. We're going to need more room than that. Bring it up here. So we're taking that equation they gave us, which, remember, is a connection between dollars and years since 95. That's what it is. So I'm plugging in $248 billion, and I want the equation to tell me the t, the time, the year, when that amount of money will happen. So I've got that little equation. I need to solve that equation for t. So we just took that 248 and plugged it in right there. All right, so remember solving from your algebra days? Best days of your life, right? T is saying, I want to be alone on my side of the wall, right? The equal sign's like a wall, so I made that straight line. The equal sign's like a wall separating the two sides, right? They're equal to each other. Left side equals right side. And the T is saying, I want to be alone on my side. Get rid of this 84 number and get rid of this 9.44 number. I want to be alone. We're trying to solve for T. So what do you do first to solve for T? Yeah, you first get rid of the 84 and you do the opposite at every step. Remember that? If something's added, you subtract. If something's multiplied, you divide. And whatever you do to one side, yeah, you have no choice but to do the same to the other. You got to keep the balance, right? If they were equal before and you treat them the same, they'll still be equal, won't they? Remember all this is coming back from your algebra days? Cancel that out there, and then we get 9.44t equals, somebody got a number there? It's 100 something. It's about as much as I can tell. Isn't it?
163.82.
163.82?
Subtraction.
Right. We all getting that okay? 163.82. Whoops, I'm still having a little trouble here. Okay, and last step to get t alone? Divide, because that 9.44 is multiplied. And you got to do both sides, so you keep the balance. T's alone, what does t equal? 17.3. Okay, I'll just say 17.35. Okay, now, so to predict the year. So should I say it's in the year 17.35? Good. Remember what T was all along. T is years after 95, right? So I've got to take 17.35 and add 1995. So what do you get? You get 2013? No, 12.35. 2012.35. Now, what kind of answer? Do they just want a whole number? Okay. Do they want 2012 or 2013? Is that what they want? They want just a round? Okay. So 2012 it is. It's in the year 2012 that the sales will reach 248 billion. Is that making sense how we did that? Questions I can answer? All is well? All right, let's move on. What number is that? Number 8. The following is data for the first and second quiz scores for 8 students in class. Plot the points in the grid below, then sketch a line that best fits the data. That's the same thing. Oop, did I
This doesn't have it for some reason.
use the line above to predict the value? Is there just nothing showing up?
It's a graph, and then it's Q1 on the bottom, Q2 on the sides, and then it counts by 4s across.
Oh, okay, so there's a graph showing up on your guys' thing, right? So you're going to have to graph, and it's putting Q1 here, you're saying?
Yeah.
And Q2 there? Yeah, so and it lets you click dots, right? Yeah, so you're gonna graph actual points. So I can just kind of mimic and show you. Basically, quiz 1 numbers go from 10 to 30, notice. So let me do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, this is 20 here. 4, 5, 6, 7, 8, 9, 30. Here. All right, so I got to go up to 30 on the quiz 1 numbers. On the quiz 2 numbers, I've got to go from 8 all the way to 28, basically same kind of thing. So all the way to 28, so here we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not going to make it at this rate. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9. So there's 28. That's all I need. It's 28 right there. Okay. So we're supposed to take that graph, and this is Q2. And then just put the various points on the graph. What do I mean by the various points? Well, the first point is right here. There are pairs that go together. So this is like the X and the Y. Because they had me put Q1 on the X-axis, huh? So you're gonna take 10. You're gonna go over 10, up 8. So over 10, up 8, right about there. That's the point, over 10, up 8. And you'll click a dot there. And then next you'll do 14, 11. So this will be 11, 12, 13, 14, 11. Be about right there. 14, 11, etc. So you just click all those dots one at a time. It's a little tedious. Make your own scatter plot by putting the dots on there. And then what's their question? Oh, use the line above to predict the value of the second quiz score if the student had a score of 23 on the first test. So there's a connection between first quiz, second quiz. So I'll let you do that. You need to basically go over to 23. Right? So in the end, you're going to get a line. You're going to get some kind of, a bunch of dots that basically sort of line up. And so once you've got that, then their final question is, find the second quiz if a student had a 23 on the first test. So if they got 23 on quiz 1, go up, 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 hit the line, and then go straight over and see what quiz score you predict on quiz 2. You see how that line is a connection between quiz 1 and quiz 2 numbers? So you'll need to find, if 23 is the quiz 1 score, go up to the line and straight over, find what quiz 2 score matches with that quiz. In other words, this is the point. Over 23, up what? Is what we're saying. This dot here, which is on the line, I just made up a line, whatever line you get, is over 23. In other words, quiz 1, 23, up how much? How much is quiz 2? So you see that a line is a relationship between two variables. It's a connection. It's a little friendship between two variables. All right, I'll leave you to that one. That's about all I can say without an actual graph here in front of me. On we go to number 9. Choose the most appropriate completion of the sentence. In order to indicate a strong correlation between variables, the correlation coefficient will be... Have I lost y'all in dots? Yeah, right. Near 1 or negative 1 or 1. Either one, huh? Right, either one means a strong positive relationship. Sorry, not positive. Strong correlation. Could be positive or negative. All right, on we go. These last ones will probably be easy for you. Looks like 8 was the hard one. 10. Question 10. If the correlation coefficient is negative, if R is negative, what does that mean? The slope of the regression line is negative. Yeah, for sure. Yeah, that's it. That was easy. Next one. The correlation coefficient R is a number between negative 1. These are easy for you. R is between negative 1 and 1.
I'm just out of curiosity. What is the first thing? Is this supposed to be infinity?
Yeah.
Oh.
Looks like they did some kind of funny...
It shows the...
Does it show the infinity? Okay, on my printout it does something weird. With the obviously, with the technology, I don't know what it is. But your guy's screen, it shows a negative infinity, positive infinity. Yeah, well, here we have a technology breakdown. Special new math symbol. All right, and then this is number 12, although here again is a tech problem. It kind of split question 12 at the dividing line of the page. Question 12. A study was done on smoking and lung capacity. 200 smokers took part in a study that asked them how many cigarettes a day they smoked and then measured their lung capacity. The correlation was found to be R is is there a negative sign? It's very tiny. Negative 0.992. Based solely on this study, it can be concluded that smoking causes lung cancer. Is that true? Is that false? Why is that false? Okay, so how about if they said lung capacity? Let's just brush that aside, because that's really not the point of the question. So let's just brush that aside. What if they said smoking causes smaller lung capacity?
The answer's to concrete.
Would that be true or false? And what would be the reason based on what we talked about in the first exam of the course? Here's a good harken back. So if two things, what they're saying, if two things have a very negative relationship, right? That's negative, not 0.992. That's pretty much a line going down. This is what is it? It's how many cigarettes a day? So number of cigarettes per day that they smoke. The more you smoke, and this is your lung capacity. It's going down, right? The more you smoke, the lower your lung capacity. So can we say that smoking causes smaller capacity? The key word here is, let me remind you of something. It's been months. It's been back when the weather was warm, hot. Back in August and September.
Correlation does not cause causation or something like that?
Yes, remember we talked about number of Boy Scouts. Remember them Boy Scouts? State by state? And number of criminals in those states. And I said there is a very positive correlation. And indeed there is. That's a true statement. Right? States that have more Boy Scouts have more criminals. If we went state by state, California, Vermont, Arkansas, New Hampshire, state by state, said how many Boy Scouts you got? How many criminals you got 20 years later? Look at that. The more Boy Scouts they got, the more criminals they got 20 years later. We would find a very positive, if we did the dots, and think about it. Think about somebody flashing that up, a Boy Scout hater, flashing that up at some anti-Boy Scout rally. Do they have such things? They have an anti-Boy Scout rally. So anyway, and they showed this guy. They go, look, it's scientific evidence, right? It's scientifically proven. Don't argue with science, right? It's just true. Look at it. More Boy Scouts, more criminals. State by state, this is scientific evidence that Boy Scouts are causing criminals 20 years later. And so what's the story? How can this graph be true? That is true. If we did the graph, it would look like that. There would be a positive correlation, but it's not causation, right? That was the key phrase. That was the most important phrase out of the first month of our class. Correlation or association. I think I said it that way at the time. Same thing, whatever. Correlation or association does not necessarily, it might, but you can't automatically assume, does not necessarily mean or imply causation. So in the case of the Boy Scouts and criminals and the bottled water and the cancer, that was the other one, right? What's the case with the Boy Scouts and the criminals? Why then this positive connection if it's not a causation deal? Why are they positively connected?
Random luck.
Not random. No, there's a reason. That's not random, right? Random would be dots everywhere. That's not random. That'll happen every time you check it. There's something causing that, but it's not the Boy Scouts. Population. Remember what we determined at that time? We said if you're going state by state, like you look at California, California's got a higher population, so we got more Boy Scouts. We also got more criminals. You go to Vermont, they got less Boy Scouts. They also got less criminals. They got less everything. They got less honest people, less criminals, less lottery winners, less everything. And we got more everything, right? So population is causing both of them. Of course, Boy Scouts and criminals are connected. They're connected by population. That's what's causing them both, right? So you got to watch out. You got to be careful. That really is super important. So just looking at this graph alone and saying, well, look, more cigarettes, lower lung capacity, therefore it's causing. Now, it has been scientifically proven to cause. It, in fact, does cause. It is true in this case, but you can't take that graph alone. They had to do an actual study. And we talked about that earlier, right? A study in which, not just observational, but experimental study, where they took people that smoked, people that didn't smoke, and they had to do a scientific study. So you can't just simply look at a graph and determine automatically causation. You got to be slow to jump to causation. You got to be careful. Two things can be connected positively or negatively, and not because of causation. Or they could be. This one, of course, is causation. They've proven it. Surgeon General has proved it quite strongly. But this alone wouldn't prove it. All right, so that's a false statement for that reason. How about number 13? I just scribbled all over number 13. It's the same thing. They're saying CO2 concentration in the global temperature, right? If we find a connection, does that mean causation? False. Again, not necessarily. Now, they can study and try to prove causation, but that's different than just correlation. So that's the point of these two examples, is to remind us that just because two things are associated, connected, doesn't mean one's necessarily causing the other. You got to be careful about that. That's probably, many statisticians say that's the greatest contribution of statistics to science in the last 100 years, is getting really clear that causation is not necessary, that the association does not necessarily imply causation. We've got to be careful. And that's the difference between an observational study and experimental study. And we don't have time to review all that right now. We better move on. We'll do it on final day when we review, because that'll be on the final. All right, question 14. Are we almost done with this? A long section. Is the equation of the regression line that relates hours per week spent in the tutoring lab then the best prediction for the GPA of a student who never... If the equation... Okay, I missed the end. If the equation of the regression line that relates hours, blah, 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 then the best prediction for a student who never goes. All right. So they're giving me this equation. Y equals 2.1 plus 0.28x. If that equation is a connection, a prediction, between hours per week in the tutoring lab, this is your hours tutoring, and Y is a GPA. Yeah, GPA. Okay, so let's just suppose that they've got that equation connecting GPA and hours tutoring. What is the best prediction for the GPA of a student who never goes to tutoring? Is it 2.1? Is that true? If you never go to tutoring, all right. So we have to plug in x equals 0 here. Because if you're never in tutoring, right, this person never goes to tutoring, then plug in 0 there. That's none of you, right? I'm just giving you a hard time. All right. 2.1 plus 0.28 times 0. So you just plug in a 0 there. And it comes out 2.1. So yeah, they're right. So the prediction of the student's GPA would be 2.1 if they never go to tutoring, according to that equation. On we go. Number 15. So another equation, y equals 8,000 plus 0.02x. What is x? Where's the rest of the line? Rest to? Income in dollars of students' parents. All right. Income of mom and dad. So income of the parents. With cost in dollars of tuition. Tuition cost. So basically, the more the parents make, the more that college is going to cost. They're going to give you less of a break. That's what this equation is saying. All right, so let's give it a try there. So is that true? And what would the slope? First off, which one is the slope? Yeah, the slope is the number next to x. So that's the slope. So it's $0.02 over 1. You always put it over 1, right? And so that means that's 2 cents, basically. Which means if this... Then slope tells us that for every $1 increase in tuition, The student's parents' income tends to be 2 cents higher. Well, it's y over x, because it's rise over run. What's y again? Y is tuition. So it's tuition. So 2 cents in tuition, $1 in parents' income. So no, they've got that backwards, right? They said $1 in tuition. It's 2 cents in tuition. False. They're reversing them. Did I do that too quick? Did you track with all that? They're flipping it on us. That's wrong what they're saying. So remember, slope is rise over run, and rise is y, because y goes up and down. Run is x, and then I just followed the y units. They told me that the parent's income is x, and y is the tuition, and so it's 2 cents in tuition for every $1 in parent's income. And they said it backwards here. They said every $1 for tuition. No, it's supposed to be 2 cents for tuition. Is 2 cents for the parents. No, it's supposed to be $1 for the parents. So that's false. They got it upside down. They were testing us. We good there? I think we're about done, aren't we? My goodness. If the equation of the regression line that relates percent blood alcohol to reaction time, so y equals 36 minus 1.3x. What is... okay, this is reaction time. And this is percent blood alcohol level, BAL. So alcohol level. Anyway, then the slope tells us, what does the slope tell us? So which one's the slope there? Negative 1.3, right? The number next to x. So that's negative 1.3 over 1. Slope is y over x. What's the y? Reaction time. So it's reaction time over x. What is x? Percent blood alcohol level. So for every percent increase, 1% increase in blood alcohol, reaction time goes down, negative 1.3. Yeah, that's true. They've got that right. How are we doing? We good? 17. If the correlation is 0, there is no relationship between the variables. They're trying to trick us. That's false. And the reason is R specifically is the linear. All it does is tell us if there's a line or not a line. I can't talk and spell. Let me do this. Coefficient. There we go. R is the linear correlation coefficient. They do have one good lesson here. So what I mean is, if things are pretty much in a pretty good line, R will be like 0.8 or something. And if things are just crazy everywhere, R will be basically 0. But what if things do some other pattern? Like maybe the dots do like an upside down U shape. They're very connected. Those definitely have a relationship, but R would still come out about 0. Because R just says, hey, it ain't a line. That's all R tells you is whether the two variables have a line connection or not a line connection. So they could have some other kind of relationship other than a line, like in this case an upside down U-shaped connection. But R will still come out 0. So just because R is coming out 0 doesn't mean that they have no relationship. It means they have no linear relationship. But they might have some other relationship. If you take higher level stats, they'll investigate other more fancy relationships instead of just line relationships. We're not going there. We're just doing line. This is introductory stats. We're just doing line relationships. All right, question 18. I think that's the last one, right? Yes, let's wrap it up. If the equation of the regression line for the days high temp X and the mean number of robberies at days Y, then on average, days with higher temp also tend to be days with a greater number of robberies. Is that true? The equation of regression line for today's high temp. So X is the temperature, basically. And Y is the number of robberies. committed in the state, let's say, that day. Then on average, if the... Oh, they didn't tell me what it is. Mine's missing the number. What does your guys say? It just says is blank. Mine didn't print. Anybody got number 18 on their screen? Well, basically, if that R is positive, it's true. So if R is positive, then that would mean higher temperatures associated with more robberies. So I'm going to assume it's positive. Probably is. So what does that mean? Higher temps cause robberies? No, they're just associated. Right? Probably people aren't going to want to be as anxious to do robberies when it's freezing cold outside. Something like that. All right, so that'd be true. I'm assuming R is some positive number there.
28.
Is that what it is?
Y equals 0.3x plus 28.
Plus 28? Yeah, this is positive, so that's a positive value. So, yep, that would be true. They have more temperature, more robberies.